The wheel shown in this figure consists of a thin hoop of mass m and radius r that contains these three triangular spokes, and the rotational inertia of one of those spokes around that pointed end is given as mr squared over 2. So we want to come up with an expression for the total rotational inertia of the entire wheel, which is going to be the inertia of the hoop plus the inertia of each of these three spokes. So we can write this as I total is equal to, now you may have to look up the inertia of the hoop since that's not given, but if you go to your table, you'll see that the inertia for a thin hoop is just mr squared, and then we've got these three spokes to add on, and the inertia for those are mr squared over 2. And I could just add that in 3 times, or I could just say, since there are 3 of them, just multiply that by 3. So this total inertia, mr squared for the hoop, and the second part, the 3 mr squared over 2 for the spokes. If you get a common denominator, I could multiply that first thing by 2 over 2, which doesn't change it. So now that when I add them together, I get a total of 5 mr squared over 2. That's the total rotational inertia for this entire wheel in part A. Now the wheel is initially at rest and held in place, but it's free to rotate around its center point, and a constant force F is exerted tangent to the hoop for a time t. So just imagine like there's a force somewhere over here tangent to the hoop that's exerted for a time t, and we want to derive an expression for the final angular speed of the wheel in terms of mrf, t, and physical constants. You can do this one or two different ways. You can go through and use Newton's second law in rotational form to get the angular acceleration, and then you can use rotational kinematics to get the angular speed, since you know the angular acceleration and you know the time. That's probably the easier way, but also the longer way to do it. A way to kind of shortcut it is to use another method, which is that the net torque is equal to the torque times the time, which I'll write down here. The torque multiplied by the time, that's the angular impulse, is equal to the change in the angular momentum. This is the rotational equivalent of saying that the linear impulse, Ft, is equal to the change in linear momentum. So we're just putting this in rotational form. So the torque is going to be the force times the radius, and we'll leave the t, the time, as it is, and that's equal to the change in angular momentum for a rotating object. That's going to be the inertia times omega final minus omega initial, where in this case the wheel started from rest, so we could say that the initial omega is 0, and the final omega, we're just the omega final, we're just calling that omega. So we have F R T is equal to the inertia, which we found up here, is 5 mr squared over 2 multiplied by the omega. You have an r on both sides, which we can cancel out, and you just want to solve this equation for the omega because it puts it in terms of all the other variables that are allowed. Now we're going to say that the wheel is rolling without slipping along a horizontal level surface with this angular speed that we called omega, and at time t equals 0, it starts rolling up a ramp. So let me draw on this diagram. This line will represent the ramp, and we want to draw an extended free body diagram for this wheel. That means all the forces have to start where they originate and then point in the proper direction. Well, we have gravity that acts on everything, and gravity always originates at the center of mass. So I'm going to have an Fg from the center of the wheel pointing straight downward. Then it's on a surface, so that force is going to be on the starting from the surface and pointing perpendicular, passing through the center of mass. So that is going to be an arrow, which is the Fn. And then finally, there's going to be a frictional force. Now, which way is the frictional force going? Well, we know it's parallel to the surface. So is it going up the ramp or down the ramp? We did this one in the notes, but just to emphasize, since the wheel is rolling up a hill freely, the angular acceleration, the angular velocity would be clockwise, because the wheel is turning this way as it's moving up the hill. But it's slowing down as it's going up the hill, which means the angular acceleration is in the opposite direction, counterclockwise. So if I just label that on this diagram, a curved arrow to represent the angular acceleration, if I move in that direction around the entire wheel, at the point where I'm getting down by the surface right here, you can see that that's directed up the ramp. So the frictional force, I'll do the arrow directed up the ramp that originates in the same place as where the normal force originated. And that's how you can also answer part D, justifying the choice for the direction of the frictional force. It's based on the fact that the wheel was rotating clockwise but slowing down, so the angular acceleration is counterclockwise, and so this frictional force is the one that gives a counterclockwise torque. So by going up the ramp, it's providing a torque that is counterclockwise, the same direction as that angular acceleration. And in part E, we want to derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until it reaches its maximum height where it's coming to rest. So this is going to be a conservation of energy. So we'll start out just by writing the Ki plus Ui equals Kf plus Uf. At the bottom of the ramp, it is moving, and at the top of the ramp, when it reaches the highest point, it's not moving. So K final is 0. At the bottom of the ramp, it has no gravitational energy, but it does have gravitational energy when it gets to the top. So we're going to write this as K initial is equal to U final. The K initial is the translational plus the rotational part. So the translational part, 1/2 mv squared, plus the rotational part of 1/2 I omega squared. All of that is that initial kinetic energy, and that's equal to the final gravitational energy, which is mgh. So if you plug in the I, which is the I from up here, and then replace this V with an R omega, so that now everything is in terms of omega, it would appear that you would have the right answer, except there's one thing that is going to mess a lot of people up with this question, and that is, what does this M represent? Because notice right now the M doesn't exactly cancel out. When you plug in the inertia equation, so I'll do this middle term first right here. This is going to be 1/2 times 5/2 big M, big R squared, or in other words, 5/4 mr squared. This M is not the same as this M or this M, because this represents the mass of the entire system, as is this M right here, but this capital M right here just represented, see, that was that M came from the hoop and also these individual spokes. So they ended up being combined together to just give you this big M right here. But notice that the hoop itself has a mass M, and then each of these spokes in the wheel also has a mass M. So the total mass of the entire wheel is actually going to be 4m. So that's what you've got to put in place of this m and this m. So we have 1/2 times 4m v squared plus the part we just did is equal to 4m g h. Now we can cancel out the m's, and you can go through the rest of this math on your own. Combine the 1/2 with the 4, combine the 1/2 with the 5/2, replace this v with r omega. Since this part of the question, the final answer has to be expressed in terms of omega, not in terms of the v, and you can solve the whole thing for h, and if everything is done right, you should get a final answer, and all I'll tell you about the final answer is that the fraction 13/16 appears in the answer, and hopefully you can figure out the rest of the stuff in the numerator and the denominator.